All right, I think we're ready. Today what we're going to do, I'm on a little bit of different setup, so I'm over on the other side of the screen from normal, and things might look a little bit normal, or well, a little bit different from normal, but I think it'll be all right. And what we're going to do is we're going to talk about the Truss Project. So this is the project that kind of, if we were in person, we would design a truss within some space constraint type things and go cut it out on the laser. It would be a wooden type truss, and we would assemble it and then test it physically. But since we're scattered all over the place, then that's not quite practical. I did try that once where like we would mail parts and then mail parts back in to people, and so it kind of worked. But what we're going to do instead is continue with our SolidWorks. I did see people are still having issues with the license server in SolidWorks. Hopefully that gets resolved, and I don't know if it's affecting everyone. So I think it could be maybe a connectivity issue. Like SolidWorks has to go online, check out a license, and then every now and then while you're still running SolidWorks, it'll still in the background kind of go and do that. So if you have kind of intermittent internet access, then one of those times it could not find the license and you'd be stuck. There is a way, if you can get connected, there is a more permanent, not permanent, but a longer term way to check out a license from SolidWorks. So you can actually go in and check out a license for, I think the limit is 30 days at a time. And so then if you do manage to do that, then you will have access to SolidWorks without having to do the internet deal. So you might look into how to check out a license long term if you're having issues. So you could go and get the license when you do have internet connection that's reliable, check it out for 30 days, or well, we don't even need it that long, but I think that's the max you can do maybe. And that way you won't have to rely on your internet connection to go and check out that license for you. So that's the thing that you could do if you're one of the people having trouble with SolidWorks not wanting to find the license server. Anyway, we're going to use SolidWorks as a team, so there'll be up to 3 people on a team, and you may all be in different places, and that's fine. You'll have to work that out. In fact, this is on the July 25th page, and there's a Truss Project Summer 2022. It kind of gives you a PDF outline of the things you're going to do. So ultimately it's a report, so a paper that you end up writing, but the core of it is this SolidWorks simulation of your truss that you have designed in SolidWorks and simulated. So that's the ultimate thing. I'll add another video. Maybe I already have one. I don't remember if I have one or not, but I'll add another video on how to make SolidWorks do that simulation for you. There's 2 main ways you can do it. One way is you can create your like physically draw the part, well, not physically, digitally draw all the parts in SolidWorks, assemble them together and put loads on it and simulate it. So you could do that. But SolidWorks has a special element that is specifically made for simulating trusses. So I'll show you both of those ways to do that for your simulation part of your truss assignment. So this document here will give you the rules, guidelines for that truss project. It's not due until the last day, August 11th, last day to turn in a report. That's talking about the truss report. Let's see. The other thing I wanted to talk about today is deflection, beam deflection. We did the integral method. So we went in and developed the radius of curvature, integrated that equation, combined with some other things a couple of times to get equation of elastic curve, and we used that a little bit. And then I think the next lecture is one of the ones where we didn't have a lecture. We've been doing exam 2 stuff lately. The exam 2 did not have beam deflection, so I wanted to do beam deflection today, some examples of it, not using the method of integration, but using those beam charts, which I guess I do need to get those beam charts ready. Where are they at? Here's one. All right, so I'll open this in a new tab so that we have it handy right there. Okay, and we're going to go through some of the web work These are in homework 17. We're going to go through some of those, and I think I was supposed to open up homework 17 longer, so I might have to add some days to homework 17. I think it might have already closed, so I'll add some days to it in case you didn't actually get homework 17 done. Because I'm pretty sure I said I was going to do that to somebody, and I forgot to do that. So homework 17 is going to come back open, and we're going to work through some of these beam deflection problems. I think there's maybe 4 or 5 of them here. I don't know if we'll do all of them, but just some of the generic ideas of how you do beam deflection by superposition. So that's our topic for today. So let's go ahead, and I did see where it says the current bit rate is lower than the recommended bit rate. Let's see if I can change that. Not sure if I can. It says the stream status is good, but normally it says excellent. So let's see if I can set that up to be a little better. I'm not sure I can. It may just be what it is. I'll try to watch and see if it starts buffering on us or not. But I don't see a way to change that right now. And it seems to be doing okay. Maybe it's not doing a very good job on the resolution, but that should be okay. All right, so what I wanted to do was work on this, start out with problem 1. So I was going to copy this and bring it over to our OneNote and see how we can do that. Oh, hold up. Maybe I can't copy it very easily. I did also just upgrade to Windows, whatever it is now, 10 or 11, whichever one it is, and haven't really gotten all of that going the way I would like for it to go. So maybe we'll just do it this way. Copy image, paste. There we go. So we'll do it this way a little bit. Let's get that on your screen though. Basically, I'm working homework 17, problem 1, at least parts of it. So we've got, that's there. So for my version, here are the details. I've got, this is an I-beam. It's an S203 by 27. Okay, so that describes, S is for standard flange I-beam. W would be a wide flanged I-beam. The only load on this guy is its self-weight. So that's the only thing that's making it bend at all, is the fact that it has weight of its own. It has a length, I assume that's A, of 12 meters. There, didn't want that to scroll. Find the following, assuming the beam is composed of structural steel. So the structural steel part is telling me that that's going to give me the density of it, but the charts that I'm going to use are assuming steel also. And it gives me the modulus of elasticity. So let's look up some of those things. E, we're going to need a, need to go back over here and go to, not that. Oh, yeah, it is that. Material properties. Let's grab some material properties and look at those. Zoom in to structural steel. And we've got structural steel, modulus of elasticity is 29,000 KSI. Okay. So E is basically 29 times 10 to the 6 PSI. We also need our, not material properties, we need our beam deflection equation eventually, but right now I want moment of inertia, so we need an S beam. This is a S, oh, this is a S203. This chart is for US units, so I need the chart for metric units. So let's actually go back and find, I don't have the metric chart unit here, but it should be one of these reference things. Let's see if I can, these are all scattered around upside down. Those are W and S, that's the wrong set. All right, so let's get the other set. Look at it. Material properties, there's more beam deflection, there's S, there we go. All right, so we need to rotate around and zoom in, and we're looking for S203. 203 by 27. So the S, you could, oh, all right, let's show this on your screen. The S here, it's like a little note at the bottom. S means standard beam, already said that. Followed by nominal depth in millimeters, okay. Then the mass in kilograms per meter of length. So the 27 number on our S203 by 27 is 27 kilograms per meter. I want to write that down on the screen. We'll get back to it in a minute. 27 kilograms per meter of length of the beam, and I have 12 meters. I will need to convert that over to newtons to create a force of some sort, but we'll deal with that in a minute. Right now I want the moment of inertia. So the column for moment of inertia is, remember, there's the XX column and the YY column. And the XX column is the one that I want. The problem doesn't tell me anything particular about using the YY. In fact, if you look really close, you've got the little lines at the top and bottom. Those are showing the flange. So that's what that's showing. I'm not sure why my cursor's not showing up, but we'll worry with that later. All right, so II, or XX, moment of inertia I, is 24. Yes. So I am writing this down on my sheet over here. I equals, what did I say, 24? No, yeah, yes, 24 times 10 to the 6 millimeters to the 4th. That just reminded me of something. When I wrote down the moment of inertia, I mean, not the modulus of elasticity, I wrote it in PSI. So we need to go get the moment of the modulus of elasticity in megapascals or gigapascals. So that's actually in this one also, right over here. So structural steel, modulus of elasticity, 200, down, it's kind of grainy over there, but 200 gigapascals is what we want. So this brings up a little point. You know, you could convert the 29 times 10 to the 6 psi over to gigapascals, you know, put it in a conversion equation or online converter or whatever. You would not get you would not get 200 gigapascals. You'd get something close to that, but not exactly. So when you're working on web work in particular, don't convert the modulus of elasticity from one unit set to another. Go back to the chart and find the number in the chart and use that number. All right, so it looks like we've got those things that we need. Okay, let's carry on with our problem statement. All right, so here's what it's saying. It's telling me it wants the deflection of the beam at B, that's the free end of this little cantilever beam, the slope at that point, then it wants some factor of safety against yielding. So that we're not going to do that one. That's more about the flexural stress. We're going to only look at the beam deflection stuff. So we're going to do part A and B. Those will be good starting ones. So we'll do part A and B here. So let's go back to our problem. Oh, no, not yet. Well, yeah, let's go over here first. So how this thing is going to be modeled is the distributed load is basically going to act like a, well, the weight of the beam is going to act like a distributed load spread out over the entire length of the beam. Wow, I need to turn the touch commands off on this screen. I'm not sure how to do that right now. So this distributed load that goes all the way across the beam is going to be the 27 kilograms per meter. And bring up some Mathcad. Where to put it? Gotta find Mathcad. There it is, down at the bottom. All right, so let's say we'll just call it L. Well, they have it A. A, lowercase a. A is 12 meters. What else do we have? Let's just say W is going to equal 27 kilograms per meter times, and we're going to multiply times G. Times G. G should be a predefined, notice it turned green. So it's, if we go over here, G should equal our 9.81 meters per second squared. So now W should be in some sort of, well, I don't want it in kilogram per second squared. I actually want it in newtons per meter, not newtons time meter, newton per meter. All right, so 264.78 newtons per meter. So that's how much this is going to, how much force the distributed load is going to apply. So we can go back over to our deal here, and we'll write a, what was it, 264.78 newtons per meter. All right, so now we've got this set up where we need to go find our beam deflection equation that looks like this. So this is a starter one, so it's kind of a much simpler one. We'll get to some more difficult ones in a second. Let's go to beam deflections. Okay, so let's zoom in a little bit. These here, top 5, those are our cantilever beams. It's kind of hard to tell, but you can see by the way they bend that those are cantilever beams. This one, the third one down, is a cantilever beam with a distributed load, evenly spaced distributed load all the way across it. This last one down here doesn't show up in your book. It is a cantilever beam with a distributed load, but the distributed load tapers off, so it's an unevenly distributed load. That one's not in your book. This one is. So we've got, what were we trying to find? We were trying to find the deflection at B, which is the free end of the beam, and the slope at B. So they have this equation in the middle, which is the equation of the elastic curve. That's like the equation that we developed a couple of weeks ago where we went in and did all the integration stuff. You could use that and just plug in x equals the length of the beam, and that would work. But they also have this maximum deflection over in the far right column, and that is, and it even labels it on the little diagram, that is the deflection at the end of the beam. So that's really what we want. WL to the 4th over 8EI. So I'm going to write that one down in our thing over here. Now, I do have to make a couple of notes. One of them is I have to know what they're calling W and what they're calling L. So what they're calling W is the same thing that we call W. It's the distributed loads size. And then L is what our diagram showed as A, the length of the beam. So that's good. Okay, so I just wrote down our equation. That should be delta at point B right there. I do have Mathcad going, so let's put this guy in Mathcad. Oops, I missed Mathcad. There we go. So delta at point B, we just call it that, equals W times L to the 4th over 8 times E times I. Now I don't have all of that stuff programmed into Mathcad yet, so let's do that. So it does have something for L. I don't know what that is, but the L we want it to have is 12 meters. Oh, I have it as A, but we'll just fix it there. E, that we looked up, that's the material property for structural steel. That was the 200 gigapascals. I assume, yes, it does know gigapascals. I, moment of inertia for the S203 by 27 beam, we looked that up and it was 24 times 10 to the 6th, and the units on that were millimeters. Oh, there we go. Millimeters to the 4th. So now Mathcad makes this much simpler. When you're doing this by hand, there's way more opportunity to do something wrong. Put in 29 million for E and mix up the units, not convert something over, forget that gigapascal is 10 to the 9th. You know, there's really a lot of ways to make errors by hand. One of the reasons I'm using Mathcad. On an exam, obviously you're stuck with by hand or a calculator, but here we have 0.143 meters. They probably want this in millimeters. Let's check. Let's find our, actually it doesn't say, we can put whatever we want. So let's go back over to here and let's put in YB. So Y is the amount of deflection. Upward deflections are positive. This is downward, so it's actually a negative 0.143 meters, if I remember correctly. Yes. All right. And let's check and see. And log back in. No. Oh, well, I didn't write 4.3. I wrote 4.2 for some reason. 4.3. There we go. All right, I said 4.3 and wrote 4.2. So we got that one right. That also shows how, strict web work is. I had 0.142 meters and it counted it wrong, but 0.143 meters, it does count right. So we did calculate 0.143 though. All right, now the slope at the beam at point B, same point. So we look at our same setup here, and this column, the first column here, this is labeled the slope at the free end for the cantilever beam. There are two slopes on the simply supported beams because one might be sloped at one angle and the other one is sloped at a different angle, so you have to label both of them. The cantilever just shows you the slope at the end of the beam. The slope at the wall should be 0. All right. So WL, I'm going to write this down. Theta is WL cubed over 6 EI. All right. I'm going to write down our answer from the other one here before I forget it. Let's go over to Mathcad. And let's put this in. So we'll put theta, oops, not in Mathcad. I don't know where I typed that. Theta at B equals WL cubed over 6EI. This one should have no units on it. It's actually radians. So you do have to be careful. I'm not sure how WebWork does radians versus degrees. So I don't know if I write a RAD or we'll find out. So let's try to put 0.16 in there. Let's see. Or maybe we can just leave it blank, with no units at all. So we're going to put for theta 0.016, and we're going to leave the units off. Oh, all right. So I used Mathcad, so I know that the answer didn't round, but it did round. And to find the other decimals, I have to select it, math formatting, and increase the number of decimals to get the rest of them. So so here's what I showed in Mathcad. I just increased the number of decimals 0.15887. So let's put that in. 0.15887. We still doesn't like, oh, it's negative. Okay. Negative slope. There we go. We have that correct now. But we're still a little bit different from what WebWork did. That could, that's probably the difference is if we go check this code, it's probably using 9.81 or 9.8. Let's see if we can see it. There it is. It's using 9.81 for the acceleration due to gravity, and we used, what did we use? 9.807, which even that might have more decimals. Let's see. Yeah, that's what we used, 9.80665. So there is a little bit of difference there when you use Mathcad's built-in G versus the G that might be coded into a WebWork problem or a homework problem or something. So that's a little bit different. Also, that number, 9.80665, is elevation dependent. So different parts of the world are going to have a little bit different value for acceleration due to gravity, because you're going to be further away from or closer to the center of the Earth. So that number itself isn't a constant everywhere. It changes depending on your location. The further away you get from the center, the smaller it gets. All right, so that was relatively straightforward. That didn't even involve this idea of superposition. That one was just going to our charts. Whoops. Going to our charts and finding the case that matched up with whatever we were trying to solve. So that's probably on exam 3. If I put a deflection equation on there, this would be a very simple one, you know, something like this, where you just go find the right case and plug the numbers into the equation. The only chance you have of getting it wrong is like I did at the beginning, where I grabbed the modulus of elasticity in one set of units instead of the set I needed. So that would be how you get it wrong, basically. Let's do one that's a little more involved. So let's look at what we have here. Okay, this one's got a little more going on. All right, so let's do this one. I'm just copying and pasting our picture here. So there. This is again, it's the metric unit beams, W 356 by 179. So it's a much larger beam than we had before. A is 8.5 meters. B 3.8 meters. And F, this point load at the end, is 63 kilonewtons. So it's not in kilograms, it's already in newtons, but it's 63. This one tells us, let's look back at the problem statement. This one says to neglect self-weight. So we don't go put the 179 kilograms per meter on top of this beam. The only time to include self-weight on a test problem is if it tells you to consider self-weight. If it says nothing, then you neglect it. And obviously if it says to neglect it, then you neglect it. So a test problem or a web work problem are going to specifically tell you to consider self-weight if you're supposed to. In the real world, you have to decide, you know, is that important or not compared to the loads that this beam is going to have to deal with. Determine the following. The slope at B, okay, so that's right at the roller. The deflection midway between the supports, and the deflection at C. Okay, so it might do us a little bit of good, possibly, to kind of draw out what we think is going to happen. So what I think is going to happen is, let's make this a little bit bigger. I think that obviously at A and B, it's connected there, and so those points aren't going to deflect. They might slope, but they're not going to move up or down. So those points, you know, they're going to do something like that. And I assume it's going to do something like this. Now that's exaggerated and everything, but that's kind of what I think it's going to do. So we don't have a beam in our little chart over here that looks like this. This one's kind of a combination of a simply supported beam, and there's this cantilevered section on there too. So what we're going to do is we're going to have to find something that gets close, and then we're going to have to modify it a little bit to make it fit our case. So first of all of these beams, the simply supported sections, they're all, well, here they are. They're all bending downwards, where our simply supported section is bending upwards. So we have to envision these things upside down. It definitely doesn't have a distributed load. It told us not to consider self-weight, so we ignore that. It does have a point load, but the point loads that they show here are in between the span. And our point load is off, you know, outside of the span of the beam. So what I think I'm going to do is I'm going to take this case 9, which is a concentrated moment applied at one support, And I'm going to turn our force F at this distance B, I'm going to turn it into a concentrated moment at B. So let's do that. So I'm going to say that this thing is sort of like this. Oh, I don't want it to snap. How do I turn snap off of here? I don't know. I'm not sure where it's snapping to the grid, and I don't really want to do that, but it'll be fine. We'll make do. All right, so we're going to put our, there we go, pin over here, our roller right here, and that F is going to become a moment here that equals F times B. And now it doesn't quite look like our picture, right? Because our picture doesn't have the point from B to C just kind of hanging out there, but we're ignoring the self weight, so we don't have to worry about the fact that that's hanging over there. And we're going to work on this part, and then when we need to do anything about point C, we'll do another thing that we'll look at. All right, so the problem is asking us is, let's see, what was that? The slope of the beam at B. Okay, so let's go to our beam deflections. Slope of the beam at B. For us, B is the point where that concentrated moment is, so that's going to be this point right here, which is labeled, and it might be hard to see. I don't know if I can get it any closer. It's labeled theta 2. So I've got this equation, ML over 3EI. I'm going to write that down on my sheet and we'll get back to it. Theta at B is going to be ML over 3EI. It's going to be a negative slope because it's going to be pointing downward. So the equation shows a positive slope, but that moment is clockwise, counterclockwise, that's shown on our reference sheet. And the moment that we have on our actual beam is clockwise. So it's going to do the opposite. So it's going to actually be a negative one. Also, L, let's go back to our sheet. L here is the distance between the supports. It's not the total length of the beam. Our beam goes from the pin out to C, from A to C, 8.5 plus 3.8 meters. That's not what L is equal to. For us, L is the length between the supports. So L equals only 8.5 meters. E, this problem, I don't think it specified material. I'm just looking, reading it, and I don't see anything about a material. So we can look here. So this is the little footnote at the bottom of the chart material. Oh, well, no, hold up. The slope of the beam slope stuff. Oh, it doesn't, it's cut off. Is it at the top? No. What about our other beam chart? A lot of times these beams, well, oh, no, we can get, this is a named beam. That's what we can get it from. So let's see. Where are W beams at? To the fourth. There, we buffered a little bit. I did catch it buffering there. So, well, all I did is I grabbed a moment of inertia out of this chart, 574 times 10 to the 6 millimeters to the fourth. All right. Okay, I think we've got all of that. Now let's go back to our setup here. I think all we need to do at this point is go to Mathcad. So for Mathcad, we'll use this same sheet and we'll just redefine everything. So M is the moment that's applied here. For us, that's F times B. So we're going to have to put values for F and B. F is 63 kilonewtons. B is 3.8 meters. That gives us a value for the moment, which I guess we could calculate there, Newton meters. Okay. And let's put in L. This is the one I was talking about where L is the length between the pin and the roller, not the whole length of the beam. So 8.5 meters. It's labeled as A on our diagram. 3, well, 3 is 3. So E is 200 gigapascals. I guess we could have left that alone. I is, that sounds weird to say, 574 times 10 to the 6th millimeters to the 4th. And then our equation for theta at B is equal to negative, because it's sloping downwards at B, m times lowercase l is what I used, over 3e I. And let's go ahead and put more decimals in there because it didn't like it last time. Negative 00591. Let's see if WebWork likes that number. Negative, oh wait, you're not looking at WebWork. There we go. Negative 0.0, forgot the number, didn't write it down. 5909. 00590. And it didn't, that's radians again. It doesn't need units in WebWork. And we got it correct. Okay, let's see what it wants next. The deflection of the beam midway between the supports. Okay, that one, I don't know if we need to plug that one in, but let's show you how you would get it. So here is our case. This is case number 9 in this chart. I think in your book it's case 8 maybe. I don't know. But notice the shape of this curve. It's not drawn wrong. It is really true that when you have this concentrated moment, the maximum deflection isn't in the middle. It's off to one side. And if you'll notice in the equation of the elastic curve, well, no, I think this is a maximum deflection and center deflection column. They give you the maximum and tell you where it's located, L over square root of 3. And then it also gives you the deflection at the center. Ours wanted the center of the span, which in this picture, that's what they're talking about, the center of the span. So not the center of the whole length of the beam, but the center of the span being the point between or the distance between the pin and the roller. So it looks like ml squared over 16 EI is going to be delta. Delta center, I'm just writing this down, equals, and again it's negative. Oh no, ours is positive actually. ml squared over 16 EI. Okay, let's go to Mathcad and plug that guy in and see what we get. So delta at center of span, oops, not O, of span, equals ml squared over 16 EI. Let's put more decimals in there. 0094167 meters. I'm going to write that down so I can plug it into WebWork. 0094167 meters. And that's positive because the way that we have this beam set up, the middle part's actually bowing upwards. So it's going to be a positive number here. So let's see if WebWork likes our positive number. 0.0094167 meters. It does, all right. Now it wants the deflection of the beam at point C. So this is where the idea of superposition, that one what we just did really wasn't superposition. It was more, I don't know, just redefining how we accounted for the load. This one that we're going to have to do now is more about superposition. So let's look at how this is going to work. So looking at our little blue dotted line of where we think what we're trying to solve for is this distance. That's delta at C, which is what they're asking for, deflection of the beam at point C. So this part from B to C kind of looks like a cantilever beam. From A to B is simply supported beam. So what we're going to do is we calculated theta B at the roller, the slope at the roller. So we know a little bit here, and we're going to combine this. Let's see, I'm trying to find a thing. So we found this. Should I draw a new picture? Maybe so, because it's kind of cluttery there. Let's draw a new one. So here's our beam, and we've got pin, roller, and force. We said that the beam bends something like that. We calculated this theta. That was theta B that we labeled. So what we're going to do is we're going to take a cantilever beam like this, basically like this, with a point load. Oh, there we go. With a point load on the end of it and cantilevered, and we're going to, let's see if this will work. We're going to take and we're going to rotate that guy, which none of these little things will let us rotate it. I can scale it, but I can't rotate. I don't know if there's a shortcut key for rotate on any of these things. I don't know. Well, I want to rotate it, but I can't seem to do that. Maybe we'll just draw it rotated. I know I can rotate it, but I don't know. I don't know. I don't want to figure it out. So we're going to take that same cantilever that we normally have, but we're going to rotate it to line up with this. So like there's our wall, there's our cantilever, and yeah, now our point load is kind of not the same direction as it was before, but we're going to rotate it down, and then we're going to apply that point load at the end of the cantilever to make it bend to line up with our blue line that I drew. So we're going to add this little deflection from the cantilever to this deflection from the slope at B. And that will be the deflection at point C. Those two together will be the deflection at point C. So not only are we going to take a cantilever beam, put a point load on it, and cause it to bend, not like rotate, but bend, but we're also going to say that, well, that cantilever beam actually started out already rotated because of the slope at B. It was already down, and then we're going to bend it down a little further. Now, yes, those are actually making some kind of arc length, so not a straight downward thing, kind of like I've drawn my deltas here. We're ignoring that little bit of difference because these deflections are really small, but yes, we're off a little bit, a tiny amount. All right, so let's see if we can get this going. I want to make sure we're not buffering. Doesn't look like we are. All right, so let's just figure out, first of all, the deflection from the slope at B, that thing that I have labeled there. That one is, we have this distance, which is, let's scroll up and see, 3.8 meters. And basically, we're just going to create a little triangle right here, a right triangle. So delta, I'm going to call this, what should we, I'm going to call it delta theta B. So delta from the fact that the beam is sloped at point B. And that's going to equal, this looks like a tangent, right? So that delta will, well, let's write it this way so I don't lose myself. Tangent of theta B equals the opposite side, delta theta B, over the adjacent side, 3.8 meters. So therefore, delta at theta B, this value, equals 3.8 times tangent of theta B. Theta B, we already found right here. Oh, I didn't write it down. Let's see what it was. That equals negative 0.0059. 591, we'll say. Okay, so let's plug that into our old Mathcad over here and see if we can come up with something. So delta theta B. Am I not on Mathcad? Delta theta B. The weird variable names, but whatever. Equals 3.8, which I don't think I ever plugged that one in. Yeah, I did. It's right there, B. So equals B times tangent of theta B. Should be able to do this like that. And it says, let's get some more decimals in there. It says this number, 0.2, I'm going to write it down, negative because it is pulling it downwards, negative 0.02245 meters. So what that's saying is that is this distance here. So that's what that distance is. Now the cantilever part, we're going to take and find our beam deflection. But this is for the cantilever beam. Even though our beam is a simply supported beam, we're going to use the cantilever section. My picture is covering it up, but it's the one in this top row. So a point load at the end of a cantilever beam. Oh, there it goes. Point load at the end of a cantilever beam. And we've got delta max, which will be, I've called it delta cantilever on my sheet, so I'm writing that down. Equals, again, it's negative, PL cubed over 3EI. Now, again, we have to go and look that what they're talking about for L. Let me move my picture here so that you can, oops, oh shoot. There we go. There we go. So L that they're talking about is the length of the cantilevered section. So for us, the length of the cantilevered section is, see if I can get back up in the corner, is B. So it's only that 3.8 meters. So we have to be careful with what we use for L. We don't always use the same thing for L depending on what equation we're using in what application. So for this problem, L is what we have labeled as B. Let's get to Mathcad and see if we can come up with something for this. Delta cantilever is equal to negative P, which I actually labeled as F, didn't I? Yeah, F. So negative F times not L, but B cubed over 3, same E, same I, oops, need a 3, E times I. That should do it. And let's put more decimals. Okay, so it says that that delta is equal to negative, it does have the negative, 0.01, bunch of zeros. We'll just do 0, 1 then, meters. So our total delta at C, so the very end of the beam, is equal to, all right, so we have a little warning buffer. Well, try to keep an eye on it. Delta theta B plus delta cantilever equals this number. So delta at C, I'm just writing them down so I can keep track of them, negative 0.03249 meters. So now if we go back to web work, negative 0.03249 meters, and hope we got it right. And we did. Got 3 green blocks. That's amazing. All right. So that's one idea of this idea of superposition. It's not maybe the most direct version of superposition, but it does give you this idea of how you can combine different cases, superimpose the effect of different forces or different cases together to get a more complicated situation than the 8 or 10 kind of cases that you have to work from. Let's see what time. We have some more time. Let's look at another web work problem and see if we want to work any more of these. If y'all have a particular one, I don't know if, yeah, there's a couple of people watching. So if you have a particular one you want to look at, put it in the chat and we'll look at that one for sure. So this one, it's kind of the same idea as what we just did. A little bit different in the sense that the cantilevered sections on here, so we can zoom in, A, B, and D, E, they are not bending. They're just deflecting. So we're ignoring self-weight, so neglect self-weight. So that means that they're not actually bending by their own weight. And the force is actually in the middle. So this one might be useful to at least draw a little bit. Now, I don't know if I want to solve all of this, but let's copy that and go over here. Make it a little bigger. All right. So there we go. So this one, looking at it, there's a couple of things that we need to point out on this one. So this one would bend. Let's look at the section between B and D first. So something like that. And then DE and AB both are kicked upwards, but they're not bending. They are just straight line. Straight line. Basically, whatever the slope is at the end of the beam, theta 2 and theta 1, that slope just carries on through the beam. It's not like this one where we tilted the cantilever along that slope, theta B, and then it bent even further. It bent further because we had this point load on the end of it pushing it down. Here, that's not happening. So these, the little extensions on the end, the little cantilevered sections, don't actually bend anymore. They just carry on at the same slope they're already at. The other thing about this one is, let's go to our equations and find it. There it is. Here. So it's this number 7 on this chart, where the point load is offset to one side. You have to be careful with it. Notice here in the middle, where'd it go? Number 7. This one. Here in the middle, they have 2 different equations for different pieces of the span. So from x equals 0 to A, where A is where the point load's applied, there's A, right there. Well, you can't, it doesn't do anything. So there's point A. You have one equation for the other part of the beam from A from X is between A and the length of the beam, L, so this little span labeled B, then you have a different equation. I think the equations in your book are, let's see if we can find, I don't remember where, oh, they are. Let's see, there's the same thing. They don't even give you the that kind of same equation. They just tell you that for the equation of the elastic, these are the maximum ones here. They have a little bit different order from the chart I was looking at. So the equation of the elastic curve, it only gives you the equation between zero, well, between the, for the longer end of the beam, you know, I guess this side right here. Now you do have to kind of sometimes mirror these. So both of these, where do them go? Both of these have the point load off on the right-hand side of the beam. Our problem has the point load on the left-hand side of the beam, assuming I is really smaller than J. It is. You can't always trust the pictures. You have to look at the numbers. But it is off on the left-hand side. So what that does is that mirrors all of these dimensions in your equation. So B is not the right-hand side of the beam. B is the smaller of A and B. So that's important with this equation. I don't know if this tells you that particularly. It does have this over here. A is greater than B. Let's see if your reference sheet tells you anything about, oh, right here. B must be less than A. It shows it right there. This one doesn't show that, but it's also true. It kind of implies it over here. A is greater than B. It's not that B and A are the left hand and the right hand side. It's B is the small side and A is the longer side. So those are two things to deal with on this problem. One is that it doesn't quite match your diagram. It's a mirror image of your diagram, so you have to mirror all the dimensions. And it doesn't work the same way as the one we just did, where the cantilevered sections aren't bending, they're just rotating. They're just rotating upwards at whatever angle is at B and at D. Other than that, it's not too difficult. It does ask you again about a flexural stress thing. This part here, the location of the maximum deflection between the supports, I believe, yeah. So here's the equation of the maximum deflection, and there's where it's located. So you can find that just by figuring out the answer to that equation. Again, L is not the length of the beam. L is the distance labeled right here between the pin and the roller. Now this problem has two, well no, that's a little roller. It's just hard to see the little wheels on it. So it's I plus J is what L is for that part of the problem. Let's see what else we have. This one is similar to what we just did with the, well, similar to this problem we just looked at, except there's only one cantilever section and there's a point load and a distributed load in here. So they both, the point load and the distributed load, contribute to making this point D move up. And I assume they want us to, yeah, the deflection of the beam at point D. Why don't we do at least that part of this one? Okay, I'm just copying it so that we can work on it. All right. So there we've got, let's put our data in here. A, I've got 6.2. Oh, this one's in US units. B, 11.3. C is 6.5. F, 596 pounds. We're going to assume that's pound force. And W is 22 pounds per foot. Again, we're going to assume that's pound force per foot. There's not a reason to not assume that. My problem gave us a W 10 by 22. And looking at this, we're going to assume that it bends down, and then when it gets to C, it kind of just kicks upward there. And we want to find that delta. That's the delta at D. That's what we want to find. All right. So this one is a really good example of the idea of superposition. So if you've seen superposition before, it might have been in a circuit problem or something like that. But the idea is that I've got two things going on. I've got a point load and I've got a distributed load. And you can have a whole bunch. You could have, you know, a point load, a distributed load, another distributed load, a concentrated moment. You could have all of these individual things that are all affecting, in this case, the beam at the same time. In circuits, you know, you've got different sources and all this kind of stuff that are all affecting the circuit at the same time, and there's an idea for superposition there also. But the general idea is that I can take the effect of each one of my sources, in this case the force and the distributed load, calculate its effect on the beam, and then just straight up add it to the effect of the distributed load. You know, I can individually calculate them and then add them together at the end. That's the superposition. So this one's a good example of superposition. It's got some other parts to the problem also. There's, I don't remember how many parts there were to it, 5 or 6 parts, 6 parts to it. We're going to do at least part C, which is the deflection of the beam at point D. Actually, that means we will also need to do point B, the slope of the beam at point C. So maybe we'll start with that. So to be more, I guess, specific about what we're doing here, we're going to do this beam, and we're going to put a, we're going to put a distributed load all the way across it, and we'll just kind of do it that way. And that distributed load is, scrolled off the page, 22 pounds per foot. And then we've got a pin and a roller. And yes, we do know that the beam continues on, but we're ignoring self-weight, and we are right now just trying to calculate this angle, theta at C. We just want to know that, only from the distributed load. So that's a very straightforward case here. Case, that's cantilever. Case 8 in this chart. Oh, wait, in this chart. So a simply supported beam, distributed load all the way across it. It only gives us one theta because both ends it's symmetric, so both ends deflect the same amount or the same slope. W, writing this down, theta C is going to equal W L cubed over 24 E I. L is the distance between the pin and the roller. So for us, that's 6.2 plus 11.3 feet. Okay, let's go to Mathcad. So we'll start a new little thing here where A is 6.2 feet, B is 11.3 feet, L is A plus B in feet, and W is 22 pound force per foot, and E is, this is a structural, it didn't, I don't think it specifically said it was structural steel, but they all pretty much end up being closed webwork. Let me open webwork again and find where we were. We were on homework 17.3, I think. Maybe it's 4, homework 4, problem 4. There it is. All right. Yeah, it is composed of structural steel. The problem statement says that. So for us, that means E is 29 times 10 to the 6 psi. And then I, this is a W10 by 22. So I'm going to have to go to our references for I-beams. And it was a W, so it's, oh, this is the wrong set. Zoom, that's way too small. W10 by 22. 10 by 22, I think it's this 118. Yes. So 10 by 22 is 118 inches to the fourth power. Trying to get on Mathcad. And I already forgot. 118 times inches to the fourth. Okay. So theta at C. This is theta at C, but it's also only from the distributed load. So we'll do C distributed equals, it's going to slope upwards, so we'll give it a positive value here, W times L cubed over 24 times E times I. We'll give that a really small number. Again, that's in radians. Now, what we want to do is we want to do almost the same thing, except only for the point load. So now we'll go in and create this little beam. And we do know that it, has this cantilevered section that keeps going, but we're ignoring its weight because the problem told us to ignore its weight. And it has a, how many pound? 596 pound point load. And our dimensions here, I'm going to need, they are 6.2 and 11.3. Oh, that was feet. Okay, and then don't need the cantilever section just yet, the 6.5 feet. All right, so this one is, we have the offset point load, off center, this one right here, case 7. Beam simply supported at ends, concentrated load P at any point, not the center. I guess you could use this for the center also and just say A equals B, but what we want is, looking at our point load is offset to the left. We actually want the slope that's further away from the point load. So in this picture that we're looking at here, that's labeled as theta 1. Okay, so this will be theta C from the point load is equal, it's going to be positive. From our equation here, it is theta 1 is P, so that's our force F, times B, the smaller of the two dimensions, so 6.2 feet, times L, the distance between the pin and the roller, which is A plus B for us, squared, minus B squared, which is the smaller, 6.2, PL squared minus B squared over 6, that looks like 61, but I believe it's 6L times EI. All right, let's see if we can get that into Mathcad. And so that should give us the slope. In our picture, it's the slope on the left end of the beam, but it's actually the slope on the end of the beam that is further away from the point load, which is what we want. So we're going over here to Mathcad. All right, we're going to call this theta at C, but it's from the point load. Whoops, equals F times 6.2 feet, which that, what did I label that? Is that A for me? Yes, A times A plus B, so that's L. Oh wait, we have an L in here, don't we? That is A plus B, yes. Times L squared, L squared, minus 6.2, which is A squared. In the equation in our chart, that A is actually listed as B. So you have to not be so concerned about matching letters, but matching geometries. L squared minus A squared, all of that divided by 6 times L times E times I. And we get a small number there. So those are the angles. So we should be able to say that theta at C, theta at C equals this one, plus this one. And I get this 0.00963 radians. So let's see if WebWork likes that. So that would be theta at C. Got to write it down. 0.00963. Let's see. Let's show the correct answers just in case. Didn't like it. Oh, 0.006. What did we type in wrong? Do we plug it in the right spot first of all? Theta, the slope of the beam at C. So we did do that, but something, let's see. Well, first let's go back to our equation here. Actually, let's make sure that, let's go to the equation that your book uses just to make sure I'm not, I don't know, got something different from what the book uses. All right, so from the distributed load, we had, they should be both the same, WL cubed over 24 EI, that's what we used. And then the offset point load is this one. And we used P, which is what we have as F, times, and we want the theta 1. So P B, now it's negative here because I think it uses, this one uses the slope, see if it says positive, oh wow, stop. Positive is from the positive x-axis and this one's on the other side, but it should be pointing upwards. So theta 1, PB, which B is the smaller dimension. Yes, so we have, what we have is actually A. So PA, L squared should just be A plus B minus B, which is the smaller dimension. Let me check what I'm writing in Mathcad. Oh, no, that's right. L squared over 6L EI. So that all looks right. But it's something with the point load because it's saying the answer is 0.006. And I've got 0.009 with pretty much all of that coming from the point load. So let me make sure that I didn't put something. Let's see, F is 596 pounds. Did I never put F in here? Oh, maybe that's a problem. Yeah, that was the problem. It was using F from the previous F value. So now we have the right number. Oh, you can't see that. There we go. All I did is I never gave it a value for F. It was using F equals whatever the last thing I said, 63 kilonewtons. That's why it was a different number. That's the danger of using Mathcad and doing multiple problems all in the same line. is if you forget to redefine something, it uses what you already had it defined as. So now we've got this 000603337. Just copy that and paste it in here and check our answers. And we're correct. So we did it all right. Mathcad, I just didn't update the value for F. Okay. So now what it wants, oh yeah, there we go. There's a correct number. The deflection of the beam at point D. Point D is the cantilevered end over here of the beam. So based on what we've already done, that's really pretty straightforward. We calculated this theta C, and then we also calculated this theta C from the point load. This was theta C from the distributed load. And so each of those, in order to get how far this point moved up, we just use a triangle. So let's just do both of those. Let's drop those into Mathcad. So where's Mathcad? There we go. So I've got, we'll call it delta D from the distributed load is equal to what I call it, theta C distributed. So these are really tiny angles. What is it? 2.067 times 10 to the negative fourth radians and 4 10,000ths of a radian. So they're really tiny. So we could just multiply the radian value times the distance labeled C, the 6.5 feet, which I should go ahead and plug in here while I'm thinking about it. C is 6.5 feet for me. So we could just do that. Or we could do an actual tangent if we wanted to. The thing about tangent of really small radian values is that they're essentially the same. So if I did the tangent of 0.001 radians, I pretty much get 0.001. And these are even smaller than that. So I can just multiply it directly times what I call it C. And we're going to do these in inches, I guess. And then we can do delta D from the point load is equal to theta C from the point load times C in inches. And then we can just do delta D is the summation of those two things. I'm just cutting and pasting is what I'm doing there. So 047 inches, going over here. Oh, it wanted more, so I put 047. It wanted 04706, which I assume if I went and even thought about doing it, but I said, no, surely not. There it is, 0470603. So let's grab that number, plug it into here, and see if it likes that better. And it does. Okay, let's see what else it's asking, and then I think we've done enough examples for now. The deflection of the beam at point B. Point B is the, well, right here. It's right under the point load. So that would work the same way, except now I've got to use the equations for right under the point load for this, and I've got to find that distance, which is, oh no, I'm going to have to use the elastic curve equation for that, because I've got the maximum deflection. The maximum deflection is not necessarily under the point load in the point load when it's offset. It is if it's in center, but if it's offset, then it's not necessarily there. So I'd have to use the equation of the elastic curve to get that, and then I would also need to plug in that same distance A into the equation elastic curve for the distributed load, add those two numbers together. Location on the beam relative to point A, which is the pin, of maximum downward deflection. So that's a little bit more of a, you got to figure out what's going on there. So what I would do with that one, I believe, is you have the equations of the elastic curve here and here. I believe I would add them together, take their derivative, find where the derivative is 0, so where it has an inflection point, and use that location to plug into the point, or you just plot them, I guess. You just plot the two graphs and find where it peaks at. Plot them add them together though. So add this equation to this equation, plot that, and find the peak. So you could either do it graphically or add them together, take the derivative of that summation, find where that is 0, so find the inflection point, and that's your peak. So that one's definitely more than you're going to have to do on a homework problem. I'm not on homework, on a test problem, but it is a good practice problem in general. And then once you find that location, you find the magnitude of it. See what our last one is here. This one's more of kind of the things that we've done. So taking point loads, converting them to a concentrated moment, take a distributed load, convert it to a concentrated moment, do stuff like that. Okay, I think that gets us some good examples for how to do point load, or well, how to do beam deflection in general. Let me think. I'm trying to think if there are some other like special cases that let me go over here. I'm not going to solve these. I'm just going to show what they would look like. So for instance, let's say got a cantilever beam. We'll just do cantilever. And your distributed load is over here. So that's not one that you really have a setup for. But you can still do it with superposition. So what you do is this one will equal, I'm going to draw them smaller over here just to save a little bit of space. No, I should draw them the whole length not to be confusing. So it's going to equal distributed load all the way across the beam. And then instead of adding, you're going to subtract. So there's our other beam. And you're going to subtract this guy. So maybe I should draw the arrows on here. These are pointing down because that's what you want, is you want this distributed load is pointing down. And this one, they're pointing up. So I guess if I point them up, then you are adding them together. And it's still the same magnitude. So when you add, these two sections, you've got distributed load W pushing down, and then that second one down there is distributed load W pushing back up, and they cancel each other out to equal this setup. So that's one that may not be as obvious to think about, but it is how that one works. Another one, we've sort of done this one, but maybe not explicitly, so let's look at it. It's also a cantilever beam. Cantilever beam, point load is not at the end of it. So how this one would work, you would take a short cantilever beam like this and calculate that deflection, so something like this, and then you would add on this piece of the beam. So this piece of the beam is basically just going to continue at this same slope, whatever slope you had right here, theta, and you can just calculate this this delta and add it to this one. And this delta here is, or well, this delta is just equal to theta times, we'll give it a b dimension, I guess. That's going to be b. Same thing that we kind of already did up here. Right here, we kind of did the same thing right here. So that little highlighted yellow section of the beam isn't bending, it's just rotating down. It's not actually bending. I don't have any, oh, here we go. So it's not doing this like bending, it's just rotating. So it's still straight, and it's just at whatever angle you were at that I have labeled theta. So those are a couple of other little cases you might want to be aware of. There will be one or two, probably just one, but one or two beam deflection problems on exam 3, and they won't be these super complicated ones, just because they start taking a lot of time, and then it kind of loses the idea of beam deflection, and it comes more number crunching. Like, can you accurately put all the dimensions and everything in and get that right, versus can you actually do beam deflection? I am going to go back and open the look. I did see that homework 17 already closed, so I'm going to go add some more time to homework 17 in case you didn't get these beam deflection problems done already. You'll have some more time to practice on them. I think in optional 3, there's probably some beam deflection in there maybe also. I don't think there were any in optional 2. All right, I think that's good for today, and we'll be back Wednesday with some more things. So a couple of things you need to do: work on these beam deflection things. Start looking for a team. So your Truss Project team. A team is not one person. So figure out, if y'all have to meet with Zoom, or maybe some of you are all in the same place, then figure out how you're going to get your team together, 2 or 3. If you have to have 4, that's okay, but no more than 4 people. I think the document actually says no more than 3 people, because 3 is generally a good team size. More than that, and you end up with somebody who doesn't really have a job to do. So try to get 3 people, but if you need to have 4 for whatever reason, that's okay. If you need to only have 2, that's okay. Don't do just 1 unless there's some really good reason to only do 1. Work on finding that team, and we'll slowly start to add in how to do some of those simulations in SOLIDWORKS. Also, if you're having trouble with SOLIDWORKS license, look into actually checking out a license long term. You may have to ask the help desk to help you with that, but that could help with your issues of not being able to connect to the license server. All right.